we're going to talk about aspects of study design. And it's important when you get data, when you're ready to analyze data, you have to ask a lot of questions about where did these data come from. In a statistics course, you might be handed a bunch of homework problems, you might be handed a bunch of output, and you just sort of plug and chug or crank the numbers out. Write in your typical sentence and say, well, I have to include the word average, I have to include the confidence interval, I have to look at alpha. But in the real world, you got to think very carefully about where did my data come from and what was the design of the study, because that's going to help you choose what analysis you need to do. So we talked in the last set of slides about the difference conceptually of having two independent groups of people. I went to Yankee Stadium and I chose a bunch of people and I measured their happiness level. I just randomly plucked a bunch of people from Yankee Stadium. And then I went to Fenway Park and I took a bunch of people, Red Sox fans, and I plucked them out randomly and I measured their happiness level. And then I could run an independent samples t-test and say, are these two groups of people, do they have different levels of happiness? And the word independence here means that a given Yankee fan's happiness is completely unrelated to a specific Red Sox fan's happiness. I can choose any person out of the group of Yankee fans. Let's say this guy, he's a Yankee fan. He's from New York. He's from the Bronx. He's 43 years old. He's a financial analyst. He wears, I don't want to stereotype. Stereotypes can be useful. All right, so there's our Yankee fan. And if I want to pick a given Red Sox fan, I don't know, I can choose this guy. He lives in South Boston. His name is Sully. On the average, the Red Sox fans might be a little less happy than the Yankee fans, but there's no evidence that there's a significant difference there. They're just a bunch of independent people. To contrast that with this, let's say that I told you, now this would be hard to find in real life because there aren't a lot of these dyads, D-Y-A-D-S. Let's say that I went out and I found a bunch of married heterosexual couples where one of them was a Yankees fan and one of them was a Red Sox fan. And then I wanted to ask, on the average, are Yankee fans and Red Sox fans, do they have different levels of happiness? So if I go out, let's say I find a man and he's a Red Sox fan and his happiness level is 80. And then I find out his wife and she's a Yankees fan and her happiness level is 82. If I want to do a bunch of these pairs, I find another Red Sox fan, happiness is 65. Yankees fan, married, spouse, they share a house, they share a checking account, they share a driveway, they share a snow shovel, they share a bathroom, happiness level 68. You start to realize that a lot of what's driving this person's happiness are a lot of the same things that's driving this person's happiness. If I showed you somebody who's happy and bubbly and excited and full of energy, and then I lined up a bunch of potential spouses and said, guess who that person's married to? You would probably not guess the miserable, unhappy, bitter person over there in the corner, because those things are related to each other. There's some sort of unique pairing that happens here. It's called marriage, right? So when you start to see the design of the situation, if somehow knowing this person's value gives you a good guess of this person's value, it's a hint that the data are paired. Whereas if I told you, hey, I know this guy Sully, he lives in South Boston. What do you think Kevin's happiness is over in the Bronx? I have no freaking idea. How am I supposed to know? They're just two independent people. They have nothing to do with each other. So this tells us a little bit about how do we know two samples are independent of each other. And these are some quotes that I got from a few statistics books. Help us think through a little bit. And then I'll tell you the real way you can tell if your sample is paired or not. It's just from a book, this guy Rosner, who says two samples are independent when the data points in sample one, let's say sample one, are unrelated to the data points in sample two. You went to Yankee Stadium, picked a bunch of people. And then you went to Fenway Park and you picked a bunch of people. Those points are unrelated to each other. Oh, but Tybor, they're all baseball fans and they're likely to be male and they drink beer. Yeah, but the actual points here, this person is completely unrelated to any of these specific people. And that's another way to say that. This is from the Triola textbook. They're independent if the way the values are selected in one is not related to the way the values are selected in the other. Contrast that to what we just said. If I pick a man who is a Yankees fan, and then I want to see the Red Sox fan that he lives with, it's the specific woman that he's paired with, right? So it's not independent. So we can think about, what does it mean when something is paired? We'll go back to Rosner. Two samples are paired. I like this. When each data point of the first sample is matched and related to, this is the word that is unique here, a unique data point of the second sample. Let's say I did a study on eye drops, and I want to see if some new eye drop can help prevent red eye after eating a lot of THC gummy bears. And I have an eye drop and I have a placebo eye drop. And what I do for my study is I take a bunch of people and I put the medication in one eye, and then I put the placebo in their other eye, and I want to compare the amount of redness between the two eyes. And Tony, are you on still?
I'm here.
Okay, good. So you see, it wouldn't really make sense to compare my right eye or my treatment eye to Antonia's, or Antonio for that matter, plus their eye. Because this eye is paired pretty well with this eye. If this one gets red, this one's probably going to be a little bit red too. If this one's going to respond, this one's probably going to respond a little bit too. Right? And so you can think about the design of the study. And this is, quote, I love this quote. When I get my third statistic tattoo, it'll be this one. The analysis must fit the experimental situation, which means you as an analyst have to ask a lot of questions about how the data were collected. You will really bug people when you start to analyze data, because you're going to ask the PI, the principal investigator of the study, you're going to ask them all sorts of questions. Well, when did you collect this? How did you measure this? Where do these data come from? How come this is missing? What does this X mean? What's this 99? You will be a pest, but you have to be. You have to be, because you have to know the veracity or the fidelity or the, what are the data actually representing in the real world? So this is some ways to conceptualize whether your data are paired or independent. I'll show you a couple examples of research situations you might see where we use a paired t-test. The first is when the same experimental units receive both treatments. You might see, this is a cool kind of study design. Let's say I want to know if one auto repair shop is charging more money than another auto repair shop. Well, one thing I could do, I could take just like 12 random cars and bring them to one, and then take another 12 random cars and bring them to another, and see if the average is different or not. But there's a lot of variability within those cars. Another thing I could do is take this same 12 cars and bring them to shop number one. Bring them to shop number one. And they say, oh yeah, to fix that, that's going to be $5,000. And I take that exact same car and I bring it to shop number two, and they say, oh yeah, to fix that is going to be $6,000. And if I do that at all 12 cars, maybe the next car is a little more banged up, $10,000, and the other shop says $12,000. I might only need to get 10, 12, 15 cars to say, oh wow, these people are charging a lot more for that service. Tybor, I don't care about cars. Okay, we'll say this is MRSA infections or hip replacements, right? So the same unit receives both treatments. That's a common thing that you see. Let me erase all this. Another thing, that may be the most common example of paired data, is what we saw when you do a pre-post, a before and an after, where each person's measurement are paired with their earlier measurement. We saw also you might have a situation where you have naturally occurring pairs, like married or cohabitating couples, or brothers and sisters, or identical twins. That's a really nice one. And then also, you'll cover this more in epidemiology because it's more of a study design issue than a statistics issue. You as a researcher might yourself decide to pair the data by matching them up in order to minimize some sort of differences. We'll talk a little bit about this when we do confounding. So you see that all of these situations, if I explain the study to you, you might say, I can't analyze that because the independence assumption is violated. But if it's violated in a very careful, specific, paired way, then you can run a paired t-test. And if you go on and take more stats class, I hope that you do, you can see that you can even look at data that is sort of more generalized than paired. You could have triplets, triads. You could have repeated measures on the same element. You could measure one person 5 times, 10 times, 100 times. And somehow the data are not independent, but we can adjust for that in the analysis. I'll tell you one more heuristic that might help for whether my data are paired or not. And you're not in Chinatown, I don't think, when you're watching this, but imagine you're walking in Boston, Chinatown, and you've participated in a study and you've already given your pre-test data and you're walking back into the lab to give your post-test data. And you get cranked and run over by a bus and dead. Totgefahren is the German word for run over and get dead by a bus. I'll ask, what is the researcher going to do with your pre-test data? Well, you're not there to give any post-test data. And if there's no post-test data, you can't calculate the difference between your post and your pre. So your pre-test data needs to go bye-bye. It's out the window. You're out of the study. That makes it clear to you that the data are somehow paired. Whereas if Sully walks out of Fenway Park and gets cranked by a bus, what do we do when we have a bunch of independent Yankee fans and a bunch of independent Red Sox fans? Do we need to throw out someone's data from the Yankees? No. All it is now is we have 12 Yankee fans and we have 11 Red Sox fans. And that's called progress.